Alright, Math 125, good morning. Today we're going to start talking about Chapter 7 in our text. The official title of this chapter in our book is Estimates and Sample Sizes. Well, if I was going to write this book, I'd probably name this chapter something else. I would entitle it Confidence Intervals, because that's what it's all about. We're going to construct intervals of real numbers with some level of confidence to estimate different quantities of interest all through Chapter 7. Alright, so there's a bird's eye view of Chapter 7. Now 7.2 in particular is entitled Estimating a Population Proportion. Okay. Let me motivate the idea here. Hang on. Alright, let's say we want to write this down. Motivation. I always like to motivate a lecture with a simple example where it's appropriate. Let's say we want to estimate the population proportion of all left-handed statistics students worldwide. We're going to estimate the population proportion of left-handed statistics students. Alright, so the idea here is, again, I've got a huge population, including all statistics students in all universities and all of time, and a certain proportion of them is left-handed. So if little p, I'm going to let little p, let me write that, and let little p equal the population proportion, forgive my abbreviations, of left-handed statistics students. And recall, because little p is a population proportion, well, we don't know much about little p except that it's between 0 and 1, right, because it's a proportion. Because we've got such a huge population of statistics students worldwide, typically we will never know little p for sure. So our goal is to estimate it. Okay? How to estimate p? That's our goal here. Since we never will know it for sure, well, the best we can do is grab an estimate. Well, what we're going to do is, well, instead of dealing with the whole population, we'll consider p hat. P hat, that's all this terminology means. I've commonly referred to as p hat, p with a little caret above it. P hat is a sample proportion. And for this example, I'm going to let p hat equal the sample proportion of lefties, left-handed statistics students. Alright, so what I'm going to do is p, little p, we'll never know. Best we can do is estimate it. We'll grab a sample, and from that sample, we'll consider p hat, a sample proportion of left-handed students. Alright, we will call p hat a point estimate of little p. Remember, little p we never know. P hat will be our best estimate, or what we call a point estimate of little p. Okay? We call it point estimate because it's going to be a single value, a single number, which may or may not be close to little p. I suppose in the end we hope that it's close. If our sample is representative of the population, hopefully it is close to the true value of p. I'll give you an example here. Let's say in a class of 26 statistics students, let's say there are 3 left-handed. I'll call them 3 lefties, if that's all right. So, p hat from our small sample of 26 statistics students, p hat, the sample proportion of left-handed students, is going to be, well, there's 3 left-handers out of 26 students total in our sample, and here is my sample proportion, about 11% or 0.1154. Okay, so we can call p hat equals 0.1154 a point estimate of little p, where little p is the population proportion of left-handed statistics students. Okay? Alright. So to compute a point estimate of p, basically you grab a sample and compute p hat. Well, as you might expect, depending on your sample, our p hat here may be a good estimate of p. It may not be a good estimate of p. There may be a better way, and in fact there is, when we consider what we call a interval estimate for little p. So perhaps a better way is to create what we call an interval estimate for little p. All right? Interval estimate, well, the common language that's evolved here is we create what we call a confidence interval for little p. Okay? Alright, and we'll do it in this way. Let me give you a visual interpretation of what's going on here. Basically, I'm going to take a sample and consider a point estimate, namely the sample proportion with some desired characteristic of interest. That's a p hat there. And what I'll do is I'll create a enveloping or surrounding interval by successively adding and subtracting a quantity called cap E, which we will call our margin of error, to p hat, creating what we call a confidence interval. Right? This is our confidence interval for p, and it's nothing more than a range of real numbers on our number line. Now the idea here is we're basing these values on sample data, and well, maybe p will land in this range, maybe p will not land in this range. The idea here is we'll never know for sure, but we can say, employing concepts of probability, that we can be certain, at least to a certain level of confidence, or within a certain probability, that little p is contained within those bounds. All right, so that's where we're headed here. We want to create what we call interval estimates for p in this section, otherwise known as confidence intervals. Alright, it involves some syntax and some new formulas, so I'm going to lay down some variable definitions and some formulas here, so bear with us for a minute and then we'll jump right into an example. Cap E is what we call a margin of error. Our level of confidence we will label with the quantity 1 minus alpha. Alright, so 1 minus alpha represents our level of confidence, and the reasons why will become evident in later sections of the text. I'll just say this for now: the typical values for our level of confidence are 0.9, 0.95, or 0.99, kind of low, medium, high levels of confidence. We'll also be talking about critical z values. Well, a critical z value we labeled with the quantity z sub alpha over 2, and z sub alpha over 2 is the positive z value. Informally, somewhat informally, it's the positive z value that cuts off a right tail area of alpha over 2 in a standard normal distribution. Let me correct all this. Z sub alpha over 2 is the positive z value that cuts off a right tail area of alpha over 2 under a standard normal distribution. So it's a z-score. Z-score that depends on your choice of a level of confidence. Okay? Alright, E, we already talked about our margin of error. There's a formula for cap E, our margin of error, and what it is, it's your critical z value, z sub alpha over 2, not p, z sub alpha over 2, times square root of p hat q hat over n, where of course p hat is your sample proportion with your desired characteristic of interest, and q hat would then be the complement of p hat. Let me write that down. P hat is your sample proportion drawn from sample data, and of course then q hat is going to be the complement of p hat, the probability complement of p hat. Okay? Alright. Our confidence interval, as we've said previously in this lecture, is going to be written up in this fashion. Basically, I've got an upper and lower bound for P. The upper bound is your sample proportion plus your margin of error, and the lower bound is going to be your sample proportion minus your margin of error. Right? So our confidence intervals are going to look something like this. Numbers high and low, creating upper and lower bounds for our estimate for P, with a little p trapped, hopefully trapped somewhere in between. Alright, the TI-8384 calculator computes this for us. Okay, so we're going to be talking about a new operator on our TI-8384 calculator, and I'm going to jump right in and do an example of this right now. I want to talk about example 3. Let me get a fresh screen here. Example 3 in our book. It's example 3. Let me get the page number for you. Is on page 334. Now I'm going to change the example a little bit, so be aware of that. I want to focus in on part B of this example. Alright, let me read through the problem with you on page 334, example 3. It's entitled Constructing a Confidence Interval, Poll Results. In the chapter problem, we noted that a Pew Research Center poll of 1,501 randomly selected U.S. adults showed that 70% of the respondents believe in global warming. The sample results are n equals 1501 and p hat equals 0.7. Alright, part B, they want us to find the 95% confidence interval estimate of the population proportion P. Let me write that down. Find the 95% confidence interval. Right? I think you'll find in most books they abbreviate confidence interval with a cap CI, so I'm going to do that here. Find the 95% confidence interval estimate of the population proportion P where P is the population proportion of those who believe in global warming. Population proportion P let me write this down somewhat informally. I'll say global warming believers. Okay? Alright, you know the story. Some people believe that global warming is happening, and some people don't believe that global warming is happening. This is all bunk. I suppose only you can decide for yourself which to believe, but we can certainly create what we call a confidence interval for those who do believe, or the proportion for those who believe. Alright, let me write down some of this given information. We are told that 1,501 people were sampled. We were told that 70%, or a sample proportion of 0.7, are what they call global warming believers. Alright? Alright, from this proportion of 0.7, I can multiply 0.7 times 1501 to get the raw number of global warming believers in this sample, and I'm going to say 1051. 70% of 1501 turns out to be 1051, so X is going to be that raw number of believers from our sample. Alright, now we're going to introduce this new operator on our calculator. We want to create a 95% confidence interval estimate. Alright, on your calculators, get your calculators out. If we press our stat button, and we found other items there earlier in the course, so we should know where that is. Alright, press the tests sub option. Alright, don't press edit, don't press calc, press tests, or scroll over to tests. And under that test option, if you scroll down, we should be able to find a operator called one prop z int. Right, on my calculator on the 83, I believe it's address A on that sublist, one prop z interval. Okay? Z because we're basing our confidence interval on a z-score. You may recall the formula for E involves a critical z value, and interval because we're creating what we call a confidence interval. So not the z-test, it's the z-interval command, one prop z-interval. Alright, when I call up that command into my home screen, the calculator prompts me for some things. Make sure I get the order right. It prompts me for an X value, where X is a raw count of subjects in our sample that have a certain quantity of interest, namely here that they believe in global warming. It's going to prompt us for an N value. Well, N, of course, is our sample size. It's going to prompt me for a C level, and of course, that's a confidence level. And when I'm through punching in those three things, I can then highlight, calculate, to actually obtain my confidence interval estimate. Alright, what's X here going to be? Well, X is 1051. That's the raw count in our sample for those who believe in global warming. What's our sample size? Our sample size is 1501. Our confidence level. Typically, your confidence level is given to you. I'm going to plug in 95% or 0.95. And if I punch that out, my calculator returns the following information. So let me write it down. 0.67702, 0.72338. On the top line, it spits out a p-hat value of 0.7001. Well, I suppose we already knew that. And it also returns a sample size, 1501. Well, of course, this is the item we're interested in. This is going to be my confidence interval estimate. All right, how I'm going to write it, and how I'll ask you to do it on test day, is like this. The lower bound for my estimate for P is going to be 0.67702. The upper bound for my estimate of little p is going to be 0.72338. And the idea here is that hopefully P will land between these boundaries, at least with a 95% confidence. Alright, so the calculator returns these confidence intervals in this parentheses notation. Both I and the author would prefer this notation, a double-sided inequality. I'll call this my 95% confidence interval for P, where little p is the population proportion of global warming believers. All right, this is constructed from sample data, and I want us to be sure we understand we're never really sure that little p lands between these boundaries, but what we can say is this is 95% of similarly constructed intervals will actually contain little p. So it's kind of a probability argument. Overall, 95% of these interval types will actually contain the value p based on probability concepts we talked about earlier in the course. Alright, so the calculator makes it quite a bit easier for us if we consider the old days when we did these by hand. Alright, I'm going to consider number 33 on page 341. This is from your homework list. Let's see, number 33 on page 341 talks about Mendelian genetics. Let me write down the page number here, page 341. When Mendel conducted his famous genetics experiments with peas, one sample of offspring consisted of 428 green peas. So we're talking about raising peas here, so I'll say there were 428 green and 152 yellow peas. Okay. And part A asks us to find a 95% confidence interval estimate of the percentage or proportion of yellow peas. So worldwide, through the annals of time, there is going to be some proportion of peas that are yellow, and we want to estimate that population proportion of yellow peas equals little p, and because populations are extremely huge, we can't ever know little p for sure, but we're going to estimate it. Okay, so that's our goal here, is to create, using the sample data, create a 95% confidence interval estimate for little p, where little p is the population proportion of yellow peas. Okay? Alright, we're going to do it in the same way we did the previous example. We're going to let the calculator take the brunt of the work here. Press Stat, press Highlight and select the Test sub-option, and again the one prop Z interval operator, call that into your home screen. Alright, prop means we're estimating a proportion, one proportion. Later on in the course we're going to talk about two proportion samples. Well, for now, one proportion will do it. Our knowledge is going to be based on a z-score. Remember, our margin of error contained a critical z-value, an interval because we're talking about a confidence interval here. Okay. All right, so we highlight that command and call it into our home screen. It prompts us again for an x, an n, and a confidence level. All right, I'm going to plug in where we're talking about a proportion of yellow peas here. So x is going to be our raw count for the number of yellow peas in our sample. Notice our sample size is going to be the sum of 428 and 152, right? Not just 428, right? Is that clear? We've got green and yellow ones to include in our sample size. So I believe that adds up to a 580. And our confidence level here is going to be 0.95. All right, so I punch this out, and my calculator returns this interval in parentheses notation. Let me write it down just like the calculator returns it. 0.22628, comma 0.29786. So we claim little p is within this range, at least with 95% confidence. Again, we'd like to see the answers written in double-sided inequality fashion. It's a bit more descriptive and intuitively pleasing, I think. Alright, so there is my 95% confidence interval for little p, where little p is the population proportion of yellow peas worldwide. Okay? Alright, so roughly you're saying yellow peas are between, let's say 23% and 30% of the population. Okay? Alright, I want to look at number 38 now. Number 38 in our text, in our homework list. And number 38 is on page 342, I believe. Alright, let me read it here. Job interview mistakes. Alright, in an account temps survey of 150 senior executives, 47% said the most common job interview mistake is to have little or no knowledge of the company. I construct a 99% confidence interval estimate of the proportion of all senior executives who have that same opinion. Alright, so let me write down some of this given information here. We've got 150 senior executives. 47% that said that the most common job interview mistake is to have little or no knowledge of the company. Alright, that's a sample proportion. Alright, so that sample proportion is 47 or 0.47, right? The level of confidence that we desire in constructing this confidence interval is 99%. Remember, the typical values are 90%, 95%, and 99%. So I'm going to say 0.99. And I think we're ready for the calculator, except for one thing. When you go to Stat and the Test sub-option and the one proportion Z interval option, when we call that command up to our home screen, the book prompts us for an X and an N and a confidence level. Well, two of these we have already. One of them we have to work a little on. The sample size is 150, so no problem there. The confidence level is 0.99. What I have to worry about is the raw number of executives who say that it's a mistake to not research the company. Well, you've got to do a little bit of work here. They don't give us the raw number of executives who believe that. They give us a sample proportion. So X is going to be 0.47 times 150, and I'm going to round this off to 71. So 47% of 150 is 70.5, and I'll round that up to 71. So my raw number for number of executives here in this sample who believe not researching the company is the most common mistake is 71. Alright, so with these three values, I can go ahead and construct my confidence interval now. And the calculator returns 0.36833 and a 0.57834. So again, I would prefer the answer in a double-sided inequality. Basically, we've got a low estimate for P in our range. We've got a high estimate for P in our range. And hopefully, the true value of P lands somewhere within those limits. Alright, well, I can say then this is my 99% confidence interval for little p, where little p is the population proportion of executives who claim the most common mistake in a job interview is not knowing enough about the company, or I'm going to claim that's not enough research regarding the company. Okay? And again, just to hammer this home again, this confidence interval, well, what are we really saying here? We're saying that 99% of similarly constructed intervals actually will contain mu, or actually contain p, our desired population proportion. So again, we are estimating population proportions in section 7.2. Alright, we've just hit the 32-minute point, so we'll call it a day. And this concludes section 7.2, estimating population proportions.